We're going to have a look at a very simple process. It's called completing the square. In order to get to it and to show its potential use, I want to start with a simple equation, x squared equals 9. In order to find out what x is, we would take the square root of both sides. So the square root of x squared is just x, and the square root of 9 is plus 3 or minus 3. Because minus 3 all squared is also 9. So that was relatively straightforward. Both of these two numbers were square numbers, complete squares. What if we got x squared is equal to 5? Do the same again. So we take the square root of each side, x equals, now 5 is not a square number. It does not have an exact square root. But nevertheless, we can write it as root 5, that is exact, or minus root 5. So far, so good. The same process is working each time. Let's have a look at something now like x minus 7 all squared equals 3. How can we solve this? Well, again, this side of the equation, we've got something called a complete square. So we can take the square root of each side. X minus 7 is equal to the square root of 3 or minus the square root of 3. And so we can now add 7 to each of these. So x is equal to 7 plus root 3 or 7 minus root 3. Let's just have a look at another one. X plus 3 all squared is equal to 5. Again, this is a complete square. So again, we can take the square root. X plus 3 is equal to root 5 or minus root 5. And now to get x on its own, we need to take 3 away from each side. So we have x equals minus 3 plus root 5 or minus 3 minus root 5. But what if we got x squared plus 6x equals 4? The problem is this x squared plus 6x is not a complete square. So we can't just take the square root. So in terms of handling something like this, we've got to have a way of getting a complete square. So the process that we're going to be looking at is called completing the square. The sorts of expressions that we had before were like this: x plus a all squared, or x minus a all squared. So that's what a complete square looks like, one of these two. So let's multiply this out and see what we get. So this is x plus a times by x plus a, and we do x times by x, that gives us x squared, and we do a times by x, which gives us ax, and then with x times by a, which again gives us ax, and then at the end a times by a, which gives us a squared. And so we've x squared plus 2ax plus a squared. Now I can do the same with this one. X minus a times by x minus a, and it's going to give very similar results. X times by x will give me x squared. X times by minus a minus ax. Minus a times by x minus ax. And minus a times by minus a plus a squared. So tidying up the two middle bits, minus ax minus 2ax, and then plus a squared. So this is what complete squares look like? They look like one of these two. Well, can I make this look like a complete square in some way, shape or form? If I compare this with this, what is it that I see? Well, perhaps one of the things I might like to have is this written as just a function, x squared plus 6x minus 4. And let's not worry too much about solving an equation. What we want to concentrate on is this process of completing the square.